Okay guys, on day 2 of differential equations, we want to focus on more AP style problems. So the first one we're going to do is this crazy potato problem from last year's test, 2017. And what made this question tough is just the wording of it. It's not really the mathematics behind it and how to solve it, but it was just the wording and trying to figure out figure out exactly what they were asking you to do. So I'll let you read that paragraph to yourself, but I'm going to highlight a couple of important parts. So the first one is this differential equation that basically this function h models the internal temperature of the potato, and so that the function h of t satisfies this differential equation. And then we're also given this initial condition, h of 0 is equal to 91. Okay, so part A says write an equation for the line tangent to the graph of h at t equals 0. So I know that in order to do that, I need a point. And so my point is going to be h of 0, which they tell me is 91 by the initial condition. And then the other thing I need is a slope. And so to get the slope, we're going to evaluate dh dt at the time when t is equal to 0. Well, when t is equal to 0, h is equal to 91. So this is going to be negative 1/4 multiplied by 91 minus 27, which ends up giving you negative 16. Okay, so that's my slope. And so my equation for my tangent line is going to be y minus 91. Sorry about that. Y minus y1. The y1 is 91. So minus 91 is equal to negative 16 times t minus 0. Okay, we want to use this equation to approximate the internal temperature of the potato at time t equals to 3. And so the way that we would do that is we would say h of 3 is approximately, and then what has to happen is that this minus 91 has to move to the right-hand side of the equation. So it's going to say positive 91 minus 16 multiplied by t minus 0, and there we have it. You can feel free to just leave your answer like that. Okay, letter B says use the second derivative of h with respect to time to determine whether your answer in part A is an underestimate or an overestimate of the internal temperature at time t equals to 3. So I'm going to show you how to do that. The first thing we need is the second derivative with respect to time. And so we're just going to be taking the derivative of this highlighted equation back up here in yellow with respect to time. And so this is going to be negative 1/4 multiplied by the derivative of h minus 27. Well, the derivative of h with respect to time is dh over dt, and then the derivative of negative 27 is just 0, and so there we have it. But what we want to do is we want to write this in terms of just h, and so we're going to substitute in what dh dt is, and dh dt is negative 1/4 times h minus 27, and this winds up giving me 1 over 16 times h minus 27. Okay, so that is the second derivative of h with respect to time. Now, how do I determine if my answer in part A is an underestimate or an overestimate? Well, I remember that the second derivative tells me about concavity. And so I want to try to determine, is this second derivative positive or negative? And that'll tell me something about the concavity of h at t equals to 3. So if I look back up here in this big long paragraph, it tells me that the internal temperature of the potato is greater than 27 degrees for all times t greater than 0. So what that means is that if h is bigger than 27, this second derivative is always going to be positive. Okay, and so what that means, so we could say, therefore, the graph of h is concave up. Okay, well, how does that help us determine if our answer from part A is an underestimate or an overestimate? Well, remember, when we first started talking about concavity, I had you memorize that if a function is concave up, where are its tangent lines? Okay, hopefully you said below. So all of our tangent lines are below the function here. That means that our answer in part A underestimates the actual value of h of 3. So we're going to say the answer in part A is an underestimate. Okay, so that's what you need to know, is that if function is concave up, that means tangent line approximations are under approximations of actual function values. And if the graph happens to be concave down, then that would mean obviously that the tangent lines are above. And so that means that every tangent line approximation would be an over approximation, since the tangent lines would be above the function. Okay, part C, it says for t greater than 10, an alternate model for the internal temperature of the potato is the function g that satisfies this differential equation, dg dt is equal to negative g minus 27 of t to the 2/3, where g of t is measured in degrees Celsius and g of 0 is equal to 91, so the same initial condition from before. It says to find an expression for g of t. So what that means is we need to solve the differential equation and get g of t is equal to. Okay, so that's what we're going to do. So I'm going to start off by separating the variables from that equation. And so what it's going to say is dg, and I'm going to apologize up front here for my g's. It's sort of hard to write a g with this pencil. Okay, so I'm going to divide both sides by g minus 27 to the 2/3. I'm going to multiply both sides by dt. Okay, so I have all my g's on the left, I have all my t's on the right, and so now we're going to take the antiderivative. Really, before I do that, I'm going to rewrite this left-hand side as g minus 27 to the negative 2/3 dt, or dg, I'm sorry, let me back up there, dg, equals to negative dt. Okay, so now we're ready to take the antiderivative of both sides. Okay, well the left-hand side looks like a u substitution, but I should be able to hopefully do this in my head, because I would think, okay, u is the g minus 27 part right here. Du would just be dg, which we already have in the problem. So we don't need to mess with any constants here. Therefore, we can just sort of bump up and divide this like we normally would. Okay, so if we increase the exponent by 1, that's going to say g minus 27 to the positive 1/3. And then if we divide by 1/3, that means really that we're going to multiply by 3, and so I'm going to put a 3 in front there. Equals to the antiderivative of negative dt, which is just negative t plus c. Okay, we're going to use our initial condition now to figure out what c is. So this is going to be 3 times 91 minus 27 to the 1/3 is equal to negative 0 plus c. And so c is going to equal to whatever this number happens to be. And if you do the calculation, then it's equal to 12. Okay, so now back up here, what do we have? We have 3g minus 27 to the 1/3 is equal to negative t plus 12. Just plugging in what my t value is there. And then the next thing we want to do is we want to solve for g. Okay, so if we solve for g, that means we're going to divide by 3 on both sides. So g minus 27 to the 1/3 is going to equal to negative 1/3 t plus 4. The next thing we need to do to get rid of the 1/3 power is we need to cube both sides. So g minus 27 is going to equal to negative 1/3 t plus 4 all cubed. And then finally, to get g of t, this is going to just be 27. We're going to add that to the other side, plus the negative 1/3 t plus 4 cubed. Okay, so that satisfies the first part of the question. So let me just be clear here. This find an expression for g of t, that's what we did right here. Okay, and then the second part of this question says, based on the model, what is the internal temperature of the potato at time 3? And so what we want to do is just substitute a 3 into our function for g. And I'm not going to do any arithmetic here. I'm just going to leave it as this final answer right here. Okay, so hopefully that makes sense to you. That was definitely the hardest question on the AP exam last year. But I think once you kind of see it worked out, you're not as intimidated by it. It seems to make sense, like what to do. At least I hope it does. I think just the hard part is getting past the wording and what exactly they're asking you to accomplish. Okay, next problem we want to work is 2015 BC number 4. So they give you a differential equation 2x minus y. It says on the axes provided, sketch a slope field for the given differential equation at the 6 points indicated. So this is what we did in the last lecture. So here's what I'm going to do. I'm going to make a table here, x, y, and dy dx, and I'm just going to find out what is the slope at all of the points that I need to find the slope at. Okay, so if I start at this point right here, that's the point 0, 2. And if I plug that into the expression for dy dx, 2 times 0 minus 2 is negative 2. And so as best I can, I'm going to draw a line that has a slope of negative 2 at that particular point. Okay, if I move down a point to 0, 1, then that's going to be a slope of negative 1. So still negative, but not as steep as before. And then if I go down here to 0, negative 1, and I plug that into the formula for dy dx, so just in case you're not clear, this is the formula that I'm plugging into to get these slopes. 0, negative 1 is going to give me a slope of 1, and so that's going to look something like that. Okay, what about at 1, 2? So at 1, 2, that's going to be 2 times 1 minus 2 is 0, so this is going to be a slope of 0. At 1, 1, that's going to be 2 times 1 is 2, minus 1 is 1, so this is going to be a slope of 1. And then finally, at 1, negative 1, we're going to have a slope of 3, if I'm not mistaken, and so that's going to be our steepest line yet that looks like that. Okay, part B says find the second derivative in terms of x and y. So let's do that first, and then we'll focus on the rest of the problem. So from that highlighted equation up there, the second derivative of y with respect to x would just be 2, since the derivative of 2x is just 2, minus the derivative of y, which is dy dx. Okay, well, it wants the answer in terms of x and y. So this is going to be 2 minus 2x minus y, which is equal to 2 minus 2x plus y. Okay, so we answered the first part of the question. Find the second derivative in terms of x and y. Now it says to determine the concavity of all solution curves for the given differential equation in quadrant 2. So we need to know something about quadrant 2. So in quadrant 2, I know the following. I know that x is negative and y is positive for every single point in quadrant 2. Okay, so if I imagine plugging in a negative number for x and a positive number for y, then think about what that expression for the second derivative is going to be. 2 minus 2 times something negative is going to make that term go back to positive, and then plus something positive is going to remain positive. And so what I notice is that this is greater than 0 for every point in the second quadrant. And so I can say, therefore, the graph of y is concave up for all points in quadrant 2. Okay, and the reason for that, again, is because the second derivative is positive in the second quadrant, because I know the x's are negative and the y's are positive. Okay, part C is sort of a review question. So it says let y equals f of x be the particular solution to the differential equation with the initial condition f of 2 is equal to 3. Does f have a relative min, relative max, or neither at x equals to 2? So let me just say this up front. They're not asking you to solve this differential equation. They're only asking you if f has a relative min, max, or neither at x equals to 2. Okay, well, I know that relative mins and maxes have to occur at critical points. So I'm going to check and see, is 2, 3 a critical point by plugging it into my first derivative and making sure that it's equal to 0. Okay, well, this is 2 times 2 minus 3, which if I do the arithmetic is equal to 1. Well, in order for 2, 3 to be a maximum or a minimum, I know that the first derivative has to equal 0. And this does not equal to 0. So therefore, what can we conclude? We know that 2, 3 is neither a max nor a min. Okay? If we had gotten 0 for the first derivative, then we would have gone on to the second derivative to see what the sign was. That would have obviously told us the concavity, and then we could have made the determination based on the second derivative test if 2, 3 was a max or a min. But once you get that the first derivative is not 0, you're pretty much done. Okay, find the values of the constants m and b for which y equals mx plus b is a solution to the differential equation. So what I'm going to do is I'm going to rewrite the differential equation right here. And we want y equals mx plus b to be a solution. Okay, well, what do I know? I know that from part b, d squared y over dx squared is equal to 2 minus 2x plus y. Okay, well, if I find the second derivative of the thing that I want the solution to be, I can substitute that in here and see what happens. So let's see here. If I take the first derivative of this, so we'll just say dy dx, this is going to equal to m. Okay, and then finally d squared y over dx squared is going to equal to 0 because m is a constant. Okay, so if I plug that information back over here on the left, then that means that 0 is going to equal to 2 minus 2x plus y. And if I solve this for y, then I get y is equal to 2x minus 2. And now you just need to go back to Algebra 1 and be able to identify which of those two coefficients is m and which of them is b. And hopefully you said that m is 2 and b is negative 2. Now there are other ways to solve that problem, part D, but that is by far the best way, in my opinion, the easiest way, and the way that makes the most sense. Okay, 2013, number 5. So it says consider the differential equation. So we're given a differential equation here, and we are given an initial condition that f of 0 is equal to negative 1. Okay, so part A says find the limit as x approaches 0 of f of x plus 1 over sine x. Okay, well, I'm just going to do some scratch work back up here. My intuition is probably that I'm going to get an indeterminate form here, but I'm just going to check, okay, and see what this limit is actually equaling. So limit as x approaches 0 of f of x plus 1 over sine x. This is going to equal to f of 0 plus 1 over sine of 0. Okay, well, I know that f of 0 is negative 1 by my initial condition, so negative 1 plus 1 over the sine of 0, which is 0, and I do indeed get an indeterminate form. And so what this means is that we're going to end up using L'Hopital's rule in this particular problem. So again, everything that I've written down so far is just scratch work, and now I'm going to show you how you should write your actual answer and how the AP exam wants you to go about this. Okay, so the first thing that you need to say is that the limit as x approaches 0 of the numerator only is equal to 0. So we know that this is f of 0 plus 1, which is negative 1 plus 1, which is equal to 0. Okay, and then the second thing we need to show is that the limit as x goes to 0 of just the denominator is also 0, and it is. And so now we can say, using L'Hopital's rule, and I'm actually going to write out the name here. No, you don't have to spell it correctly, but it's a good idea just to write down the full name there. We can say the following, that the original limit that they gave us, limit as x approaches 0 of f of x plus 1 over sine x, is equal to the limit as x goes to 0 of the derivative of the numerator. So the derivative of the numerator is f prime of x over the derivative of the denominator, which is cosine of x. Okay, well, when I'm trying to evaluate this limit to find what f prime is, that's this differential equation back here. F prime is dy dx. And when x is 0, y is negative 1. So again, I'm going to do maybe some scratch work over here. So I know that dy dx evaluated at the point 0, negative 1 is going to be what? Negative 1 squared multiplied by 2 times 0 plus 2, which is 2. And so I get 2 for that. That means over here my numerator is going to be 2 divided by cosine of 0, which I know is 1. And so my answer is 2. Okay, so I know we haven't talked a ton about L'Hopital's rule, but hopefully you get the idea there that whenever you have an indeterminate form, 0 over 0, then the limit is just the limit of the derivative of the numerator over the derivative of the denominator. Okay, we're going to skip part B for just a second and come back to that after I talk to you more about Euler's method. And we're going to move to part C here for just a moment. So we're going to actually find y equals f of x, which is the particular solution to the differential equation with the initial condition f of 0 is -1. So so we can see it, I'm going to rewrite the differential equation here. I know that I need to separate my variables, so that means on both sides I'm going to divide by y squared, and I'm going to multiply by dx. Okay, well, I'm going to rewrite the left-hand side as y to the -2 dy equals to 2x plus 2 times dx, and now I'm ready to take the antiderivative of both sides. Okay, so the antiderivative of y to the -2, I increase the exponent by 1, so it becomes a -1. I then divide by the new exponent, so dividing by -1 puts a negative there. And then y to the -1 is just 1 over y. Okay, this is going to equal to the antiderivative of 2x plus 2. So that's going to be x squared plus 2x plus c. Okay, if I find my c value, that's using my initial condition, f of 0 is equal to -1. And so I'm going to come back up here at the top. That's going to be -1 over -1 is equal to basically 0 plus c. And so I see pretty immediately that c is equal to +1. So I have -1 over y is equal to x squared plus 2x plus 1. The first thing that I need to do is get rid of the negative sign. So I'm going to make this 1 over y is equal to -x squared plus 2x plus 1. And then to get y by itself, so that it says just y and not 1 over y, we're going to take the reciprocal. So y equals -1 over x squared plus 2x plus 2. And obviously there are several different ways that you could write the answer to that. This is just one possible way. But any way that is mathematically equivalent to what I boxed here is going to be just fine. Okay, now I want to talk to you about Euler's method. Euler's method is a way to approximate numerically the solution of a differential equation. And so what we do is essentially do a tangent line approximation either 2 or 3 times in order to approximate the function value of a solution to the differential equation. So let me tell you what I mean here. We're going to do 2 tangent line approximations, and we're going to start with f of 4 is equal to -1. So this is our initial condition for this particular problem. Here's our differential equation, dy dx is equal to x plus y. Okay, so I'm going to write a tangent line at that point for -1. So at 4, -1, I'm going to write a tangent line. Okay, well hopefully you're thinking in your head, I need a point and I need a slope. So my point is going to be 4 and -1, so I'm just going to go ahead and plug that into my tangent line. And then in that little space, I need the slope. So maybe over here I can just do some scratch work and figure out that the slope at the point 4, -1 is just going to be x plus y, so 4 plus -1, which is equal to 3. So this is going to be a 3 right here. Okay, now, what does this really say? This says use Euler's method starting at x equals to 4 with 2 steps of equal size to approximate f of 4.2. So if I'm going to take 2 equal steps from 4 to 4.2, then that means I have to go from 4 to 4.1 to 4.2. That means I would take 2 equal steps, 2 steps of equal size to get from 4 to 4.2. So how far did I go each time? I went 0.1. Okay, so my delta x in this particular problem is 0.1. But you don't really need to know that. Really, all you just need to focus on are these values right here. So the first thing I'm going to do is I'm going to use my tangent line that I found here to approximate f of 4.1. So f of 4.1 is approximately, okay, from this tangent line equation, I'm going to solve that for y, so that means I'm going to move over the plus 1, and then I'm just going to plug in 4.1 for x. So this is going to be 4.1 minus 4, okay, which is equal to -1 plus 3 times 0.1. Well, remember that was my delta x from before, so I know that I should have had that. and then this is equal to negative 1 plus 0.3, which is negative 0.7. Okay, so now I have a new point to make a tangent line at, and my new point is 4.1 and negative 0.7. The negative 0.7 was the approximation of f of 4.1 that we got from our tangent line. So now I'm going to make another tangent line. So this is going to be y minus the y-coordinate, so that's going to be plus 0.7, is equal to the slope. Well, we don't know what the slope is right now, but we can calculate that here in a second, and then times x minus 4.1. Okay, over here on the side, I'm going to calculate what the slope needs to be. So the dy dx evaluated at 4.1 and negative 0.7, well, again, dy dx was just x plus y, so 4.1 plus negative 0.7 is 3.4, and so this is going to be 3.4. Okay, now, to find f of 4.2, we're just going to approximate using this new tangent line that we found. All right, so this will be negative 0.7. I just basically subtract this term to the other side, and then plus 3.4 multiplied by 4.2 minus 4.1. And that is perfectly fine to leave as a final answer. The reason that I had to calculate this number back up here, this let me use a different color since I already highlighted it once. The reason I had to actually calculate that number is because I had to use it in a future calculation. But you don't have to use this number in a future calculation. This is your answer, and so you're more than welcome to just leave that as your final answer. Or if you did the arithmetic, again, you're not going to get any extra credit for actually solving that and finding the actual number, but it would be negative 0.36. Okay, now we want to come back to this problem and solve it using Euler's method. So use Euler's method starting at x equals 0 with two steps of equal size to approximate f of a half. So what that means is if I'm trying to go from 0 to a half with two steps, that means that each step is going to have to be a quarter. Okay, so I'm going to have to go from 0 to a quarter and then to a half when I take my steps. Okay, so the first thing that we're going to do is we're going to create our tangent line at our point 0, and let's go back up here and see what our initial condition was. It was negative 1. So we're going to make a tangent line at 0, negative 1. Okay, well that's going to be y plus 1 is equal to our slope. Well, we already calculated our slope at 0, negative 1. That was back up here. Oops, oh my goodness, I just erased it. We don't want to do that. Let's undo that. We want to highlight it. So here is the slope that we calculated in part A. So this is going to be 2 times x minus 0. And then the first value that I want to approximate is f of 1/4. So f of 1/4 is going to be approximately negative 1 plus 2 times 1/4 minus 0, which is the same as negative 1 plus 1/2, or negative a half. Okay, and so that gives me, I'm going to just sort of bullet point this. Now I'm going to bullet point this next part. That gives me my next point, and so now I want to find a tangent line at 1/4 comma negative 1/2. Okay, so hopefully you guys are seeing where that's coming from. Here's the x-coordinate, and here's the y-coordinate for my new point that I want to find the tangent line at. Okay, so the tangent line at this point is going to be y plus a half is equal to, we need to figure out what the slope is, so we'll do that here in a second, and then x minus 1/4 will be here. And so let's come over to the side of the page and figure out what dy dx at the point 1/4 negative 1/2 is. Well, remember our equation for dy dx was y squared times 2x plus 2. So y squared is going to be 1/4, and then 2 times x is going to be a half plus 2. And so this is going to end up being 1/4 times 1/2 plus 2 should be 5/2. And so this is going to be 5/8. So that's my dy dx, 5/8. There's my slope for my second tangent line. Okay, so now we want to approximate f of 1/2. So this is going to be approximately, we're going to move the positive 1/2 that's right here to the other side of the equation. So this is going to be negative a half plus 5/8 multiplied by 1/2, that was my x value, so again, this is the x value that I'm plugging in for x into my tangent line, minus 1/4, and this right here is good enough for the final answer. Okay, so I know that was sort of a long video. We're working on 30 minutes now, but hopefully everything is clear. I hope you guys are having a great time in San Antonio, and for anybody else watching this video, I hope that it has helped you out. And please feel free to let me know if you have any questions. See you guys soon.